Hello, can you hear me okay? Great, you got my slides up. So, if I could invite everybody to come in and take their seats, we're going to try and make an on-time start this afternoon for the industry panel session. We've got a lot of material to go through because it's such a big topic for which there's a lot of interest. And we've got some excellent panelists. So my name's Roger Cracknell, and I'm going to be your moderator this afternoon. And just to say a few sort of introductory words before I introduce my panelists. I think the context of this is that many jurisdictions throughout the world have set net zero targets in place. And the question is how those are going to be met. Now, one important factor about net zero is the concept of net zero embodies the fact that we can actually sequester carbon, store it underground or plant trees, as well as take the carbon out of the fuels that we use as well. So it's important to recognize that concept of net zero. I think the other important thing to say is that, and that will become apparent through the contributions of the panelists, that not all modes of transport are amenable to electrification. Arguably, passenger cars are more amenable than other modes, but certainly things such as aviation, as the panelists will tell us, are particularly difficult to electrify. And indeed, there's a word, we've got decarbonization in the title. It may not even be possible to decarbonize transport. So possibly defossilization is a better term, in which we actually use biogenic carbon rather than fossil carbon. That's another topic that we can talk about. And finally, I think that when we discuss it, we've got a panelist here, Sergey, who's going to talk about some of the safety aspects of battery electric vehicles and other fuels, because we've got to make sure that any fuels that we use are as safe as those that we use currently. So I'm now going to introduce the panelists. If I could just go through the slides. If I could have the next slide, please. In fact, that's me. Hopefully you've read that by now. I work for Shell, which, as many of you will know, is an oil company. The first speaker is Keith McManus from GE Research, who's not able to be with us this afternoon. And he's a technical manager for Combustion. So Keith will be online shortly. He's worked for GE since 1999. Then we've got Steve Ciatti, who's on the panel in front of me. Steve works for the Packard Technical Center in the US. And I think Steve has a particularly unique perspective, if I may say so, because he spent a lot of his working life working on internal combustion engines. But now he works on batteries for heavy-duty vehicles. So I think probably no one in the world has probably got such a unique perspective as Steve. And then we've got Nakata-san, Koichi Nakata, a highly respected contributor from Toyota Motor Corporation, who's the general manager for the Carbon Neutral Development Division. And unfortunately also he can't be with us in person today, but he's joining us via Zoom. And you can see there some of his biography. And then we've got Ruud Eggels, who we're also lucky to have with us today as well, who works for Rolls-Royce in Germany. And he's worked for Rolls-Royce since 1997. And he's also a member of the board of directors of the German section. And like me, he's a director of the Combustion Institute. And finally, last but not least, I'd like to introduce Sergey Dorofeev, who's the Vice President Research Director of Fire Hazards and Protection at Factory Mutual Global, FM Global. And Sergey will provide that context in terms of the safety of alternative transport fuels. So, with that, I'd like to hand over to Keith, if I may. Okay, Keith, you're good to go.
Okay, thank you.
I think I just want to get the guys on, if they can do Keith's first slide. Okay. There we go. I think we can see your first slide, Keith. Industry.
Can you hear me?
Yeah, we can hear you.
Okay. So I'm going to be talking a little bit about decarbonization as it applies to the airline industry, air transport. And the first chart I wanted to show is really the decarbonization goal for the industry. And there are a few different curves that I've broken into here. The one with the highest CO2 emissions is pictorially how we think we can get to zero carbon by 2050, which is the goal in the International Air Transport Association. So there's a number of different components here. There's, well, CO2 trajectory, if no improvement from today, is the top curve you see. Then the other way we're going to reduce carbon emissions is through technology improvements to improve efficiency of the engines and the aircraft. The traffic management and infrastructure we feel can be improved to also reduce emissions. That's things like runway operations and how we manage the infrastructure at airports. Then there's two green bands, one alternative fuels, and then going to 100% alternative fuels. Those two components really drive the reduction in CO2 emissions down to where we need them to be. Now, there's also the yellow band discussing the carbon offsets. We feel that carbon offsets are also going to have to be implemented in order to drive CO2 to zero. So I think we can go to the next slide. So I mentioned technology and improvements in technology. This slide describes a few of those areas that GE is certainly active in terms of developing technology. Hybrid electric that's an area we've been involved with for some time, and this is where electric power would be used at least during part of a flight. Perhaps takeoff would be accomplished by using jet engines to augment the electric system, and then perhaps when you're in the cruise mode, you might be able to turn off the jet engine and just run the electric motors with batteries. And that's just an example of how hybrid electric may work in reality. Now, the center picture, the CFM Rise, that's a joint effort between us and CFM, or Safran Aircraft Engines, to improve efficiency of jet engines. And we do that by going to a more compact, efficient core, and also this open fan architecture. So we feel that by going in this direction, by using advanced thermal cycles, the open fan and compact core, we can get maybe up to 20% better fuel efficiency than what's state of the art right now. And lastly, but certainly something that we're taking very seriously, is actually running jet engines on hydrogen. And we're involved in a consortium or a partnership with Airbus. And you probably read about their Zero E program, where they want to flight test a hydrogen capable engine by later this decade, actually. So let's go to the next slide. And you can skip to the next. Now, I just wanted to spend a few minutes, as I mentioned in the first chart, a large part of decarbonization for aviation is going to be accomplished through sustainable fuels, alternative fuels. So SAF, sustainable aviation fuel, it's kind of a broad term used to describe a number of synthetic fuels that are being studied and some implemented in the industry now. So we have two types of SAF that we talk about. Drop-in SAF is a version of sustainable aviation fuel. It's usually a blend of a synthetic fuel with jet A. They're called drop-in because they have gone through rigorous testing and have been approved for use without any restrictions. So there are aircraft flying around with these drop-in SAF fuels, which behave in nearly every respect. Can you please go back to the previous chart? Thank you. Now the non-drop-in SAF, we expect at some point there will be SAF fuels that will probably require some design changes in the combustion system. And in the list down below, I've put little flames next to the properties that we anticipate may vary depending on the SAF blend, the feedstock, the process used to make it. These particular properties are definitely going to affect the combustion process, and it's likely that we will have to do a fair amount of technology development and testing to accommodate the range of property variation that we're anticipating. So I think we can go to the next slide now. So, and to give you an idea of some of these fundamental processes that will, that definitely affect combustion performance are shown here. So there's a number of different properties or different processes that have to occur, like the formation of a liquid spray, injection of that fuel into the combustion chamber, and other processes that will be affected due to changes in the fuel properties. And so we're mapping from the left column to the right column what we feel these different changes in fuel behavior will affect on the combustion side. And the graphics on the right-hand side give some examples for how we believe SAF may affect existing combustor components. So you see the sprays at the top of the graphic show a very nicely atomized spray on the left, and on the right-hand side, please go back. You see a streaky spray that could be the result of variations in the fuel viscosity, the density, surface tension, etc. Can we go back to the previous slide, please? Thank you. Down below, we know that cetane number is important in driving certain effects like auto ignition or ignition delay time and auto ignition. So we know high cetane number produces a risk in that area. And some SAFs may perform or may have higher cetane numbers due to their composition. The last two pictures, we also know that due to the composition of many SAF fuels, they're they have a lower tendency to produce particulate matter emissions. And those are pictures of looking at the flames inside the combustion chamber. On the top, a Jet A example where you do see sooting and radiation from that particulate matter. And on the bottom picture, that's an example of a flame in a SAF fueled combustor. We can go to the next now, please. So a couple thoughts just around design implications. I think certainly some level of fuel standards will need to be imposed to keep certain properties within boundaries that we feel need to be established. But there may be other things that can be done to create or to design combustion systems that may be fuel tolerant or fuel variation tolerant. And so just a few thoughts on this chart around what we might be able to do. Have fuel nozzles that are tolerant to variations in the fuel properties and produce a well-atomized spray for a variety of fuels or SAF fuels. Maybe we optimize combustion chambers or combustion systems so that they operate well, they operate acceptably with sort of a bad fuel, if you want to think of it that way. But so I think versatility of the combustor to fuel variation may be something that we really need to bring into the picture. There are other things like corrosion, durability of the systems over long periods of time. Many of these things are unknown simply because SAF has not been in use for that long. I think the next slide, please. Certainly emissions regulations are an important thing to keep in mind and to make sure we're ready to address. The ICAO is the organization that sets emission standards for aviation, for commercial aviation. And so they regulate all these species, CO2, CO, unburned hydrocarbons, NOx, non-volatile particulate matter, noise, and smoke. So it's all these emissions are regulated, and we do feel, or we do expect them to be impacted when we change the fuel and move toward SAF fuels. Just a few points. Ground NOx and particulate matter low in the atmosphere affects local air quality, and that's why it's regulated. Now, cruise NOx and non-volatile particulate matter, they can affect the climate because when they're emitted in the upper atmosphere, they force a greenhouse gas effect. Could you please go back to the last slide? Last slide, please. So I'll just keep talking. So we know SAF fuels can have a tendency to emit less particulate matter. That has an implication in aerosol formation and contrail formation. So we actually expect that SAF may reduce certain emissions and contrail formation. I guess with that, I'll stop.
Thanks very much, Keith. If anyone's got any questions for Keith, can I ask them to just store them up until everyone's finished, and then we'll ask the questions to the whole panel. But thank you very much, Keith. So.
Thank you.
I'd like to invite now Steve Ciatti, if he would come forward and give his presentation. And again, think of questions for Steve, and we'll do them at the panel session at the end.
Do we use this, or do they move them forward?
Yeah, you can use that. That should work. Well, they need to stick your first slide up, though.
There we go. Excellent. As Roger had mentioned, my name is Steve Ciatti. I'm the principal engineer, well, for battery systems now, but this slide is a little bit dated. I was the principal engineer for advanced engines at the PACCAR Technical Center. And today I'd like to give you some view into the opportunities and challenges for energy and emissions reduction from advanced heavy-duty vehicles. So the first question I often get is, well, who in the world is PACCAR? And PACCAR, as I like to joke, is a bank that builds trucks and sells them to accountants. PACCAR is a company that owns several different truck brands. You've probably heard of those: Kenworth, Peterbilt, and in the EU, DAF. So here's an example of some of the trucks that we make. In the 6 to 16 ton range, you can see on the left are our medium duty trucks. The DAF brand is on top, Peterbilt in the middle, and Kenworth at the bottom. We make a variety of vocational trucks, work trucks, such as cement mixers and dump trucks and refuse trucks. And in the 16 plus ton category on the right, those are the semis that you're accustomed to seeing out on the road. Those are the Class 8 long haul trucks that most people associate with heavy duty trucks. But the intent of the slide is to show you the breadth of the different types of vehicles that we make. I would argue that compared to most auto companies, we make a wider variety of vehicles with a wider variety of powertrain needs and application and wider variety of demands than most auto companies do. Our trucks are used as far north as Yellowknife, Northwest Territories, and as far south as the Panama Canal, and in DAF Brazil and South America as well. So the conditions that they encounter, the work that they do, the fuel quality that they see or don't see is widely variable. This is not a very new slide for anyone, but I include it just for grins and giggles anyway. CO2 is obviously a pathway where if we don't make some changes sooner versus later, the numbers get to be very distressing in a very short period of time. There are very few models that predict that CO2 will be on track to satisfy the Paris Agreement, and the obvious conclusion is that a reduced energy carbon intensity is required. So there are three pathways to net zero greenhouse gas emissions, whether it's use of electricity, and that's a double-edged sword in that the electricity needs to be generated from something, preferably something that isn't putting carbon into the air. Green fuels, and the devil is in the details with the processing of these fuels, and hydrogen gas. So minimizing CO2 from fuel production and CO2 from the vehicle life cycle and CO2 from the tailpipe. So we have to account for even manufacturing and disposing of the vehicles with our CO2 footprint and their use basically while the vehicles are within customer use point. And we also then have to maintain acceptable productivity, operating cost, and infrastructure cost. Someone once asked me who the first adopters of our EV trucks are because they were wondering if we had any Tesla type first adopters in our marketplace. I said, no, the people that buy our trucks make money with those trucks. There's no such thing as somebody buying one of our trucks because of its coolness factor. That customer does not exist. If you know any of them, please send them my way because we have trucks for them. But to this point, they're looking strictly at the bottom line. What do we pay for this truck? Does it operate every day it's supposed to? Does it cost me what I expect? And does it do the job I pay for? And if those questions, any of them are no, they don't tend to buy our trucks. It's pretty simple. So one thing I like to do to an audience that is not familiar with transportation, and I've been, as Roger mentioned, I've been working in transportation professionally since 1990. I started in the aircraft business as a propulsion engineer at an airline. So if it burns fuel and moves, I've probably put a wrench on it. We're accustomed to thinking about fuel economy as consumers in miles per gallon or liters per 100 kilometer, depending upon where you live. That's a horrible metric when it comes to freight transport. So one of the ways we like to look at it is freight efficiency. How many ton miles per gallon can we move things? Most Class 8 trucks top out at 80,000 pounds, so it's on the order of 40 tons. If you take a look at the freight efficiency of a light-duty vehicle, it's pretty poor by comparison. The truck is an order of magnitude better, and rail is about a factor of 3 better than truck. So these vehicles genuinely are freight-moving modes of transport. The energy density of the storage and the power density of the unit that provides the power become of critical importance. Electrification isn't always simple. Depending upon where you live in the world, or even in the United States, the grid carbon intensity matters a lot. And if you're out on the West Coast like we are, most of our power is hydro, so it's relatively easy to get relatively clean power. But I'm from the Midwest. If you take a look at what the Great Lakes region and the middle portion region of Missouri and Arkansas look like, you would actually be less carbon intensive driving a diesel-powered vehicle than an electric one, just simply because of how grid carbon dependent it is. Now, that's probably not always going to be true, but this data is recent in that I just pulled it up here, and this data goes back maybe about 6 months. So this graph is still fairly recent. It matters a lot where you live. Considerations I had to now account for in working in chasing electrons around electrochemical circuits. How much battery capacity can we put on the truck? How much does it weigh? How much does it cost? And when you start running the numbers and doing the math with the technology that we have today, anything where the vehicle travels more than 300 miles becomes very, very challenging with today's technology to make into a BEV. Our assumptions are roughly 16 pounds per kilowatt hour and roughly $200 per kilowatt hour as far as cost goes. So that means that Class 8 long haul really isn't part of the equation. Those are likely to be liquid fuel powered for the foreseeable future because we simply cannot, with the weight and size restrictions and battery technology as it exists, fit enough energy on board the truck to get it the range that it needs to carry the payload it carries. So this is partly where we are going to have a mix of technologies in this area. As a result, we've taken a look at the different types of trucks we make and what some of these technologies may look like. So when you look in the green striped areas, the weight essentially is the vertical axis. How much city driving is on the horizontal axis. Our medium duty trucks, as you can see, are likely to be BEV, coming up in relatively short time frames, probably 2027 to 2030. That blue line in the middle is sort of the great unknown region. Some of it may be hybrid electric, but a hybrid electric can also mean fuel cell and not just engine. Each one we sort of look at in the same way. Fuel cells are not very good with regard to load following. They don't do load response well, so we would have to have a battery system to absorb capacitance. And then when you look to the far right, that would be what we would call a mild hybrid, a low voltage electrical system to take care of engine accessory loads, such as air conditioners, pumps, things of that nature. But it would still be liquid fuel. So when you take a look at the percentage driven in the city and the weight, you can see that for the longer haul trucks that have higher weight, those are likely to still be some form of liquid fuel. The challenge then is going to be meeting emission standards and meeting greenhouse gas, because those regulations don't change. Then we get the opportunity to deal with IC engine bans. And unfortunately, nobody asked me or cared whether or not I thought it was fair, whether or not I thought it made sense, whether or not I think that these solutions or these target regulations are reasonable. Our company is tasked with being able to meet the regulations as they're written, or we don't sell trucks. So the plan here is that regardless of whether or not we like it, there are certain areas of the world where we are going to have to make a reliable, relatively inexpensive vehicle that fits these criteria. And that's how we make money. We sell trucks. So we don't get the largesse to basically complain about it. We have to figure out how we're going to make the technology work in a way that's suitable for our customers. So to summarize, there are regulatory and market pressures that are changing the freight transport business drastically. And I think the other panelists will probably agree that these are not consumer-driven or customer-driven market changes. These are regulatory-driven market changes. We need advanced technology to hit these targets, and the well-to-wheels analysis is critical to ensure that we don't follow the wrong path. Greenhouse gas and ZEV at the tailpipe regulations are likely going to force our solution choices. The technology needs to fit the application and meet our market constraints. Total cost of ownership, which is TCO, and uptime. Every day the vehicle's not available is 5% fuel economy to our customers. Most important factors to our customers. Heavy-duty truck industry is investigating all of these technologies and even some that I can't talk about. And solutions that seem like a slam dunk aren't always so, in every direction. And with that, I'll close my presentation. Thank you for your attention.
Thank you very much, Steve. And I'd now like to invite our other virtual presenter, Dr. Koichi Nakata from Toyota, to speak. If you could get Nakata-san's slides up.
Thank you very much.
Hello.
Hello. Please go to the first slide.
Okay. Would you like to start your presentation? And then please just ask for next slide when you want to move it on. Thank you.
Thank you. Anyway, thank you very much for your kind introduction. It is my great pleasure to have the opportunity today to present the future direction of the internal combustion engine. Next slide, please. This is my introduction. I'd like to skip this slide. Next slide, please. This slide shows the history of power sources for passenger cars. First, the utilization of steam engines started at the end of the 18th century. Then electrification technology was used. However, electrification was replaced by the internal combustion engine around 1900s. Since then, the internal combustion engines has been a principal power source for passenger cars. At the end of the 20th century, hybrid vehicles were introduced to the market. Since then, HEV has been contributing to the reduction of GHG. And in the beginning of this century, BEV and FCEV appeared on the market. Today, I'd like to talk about the future options to realize carbon neutrality. Please go to the next slide. This slide shows the options we consider. The future direction depends on the progress of renewable energy. Renewable energy brings benefit to our life. On the other hand, renewable energies have some issues. I'd like to talk about issues to be solved. One issue is most renewable energies are unevenly distributed. In the case of wind power, the areas in high latitude have a large potential. For example, North and West Europe and the southern part of South America are suitable areas for wind-generated electricity. Solar power is also unevenly distributed. Therefore, we have to consider the options which are suitable for each area. Another issue is fluctuations. As for renewable energy, we have to consider 4 factors: production, transportation, storage, and utilization. Electricity generated from solar energy and wind energy always fluctuates under the influence of clouds and wind. And increasing electricity generated from solar energy and wind energy will lead to increased surplus in electricity sometimes. To correspond to fluctuation and surplus, storage and transportation play indispensable roles in the energy cycle. It is well known that one effective measure of storage is battery. Another measure is to convert the electrical energy to hydrogen. Hydrogen itself can be used as an energy source for mobility and converted to another type of energy, such as synthetic fuels. These fuels are easy to handle from the viewpoint of transportation and can be a solution to correspond to an even distribution of energy. Next, I will talk about the biomass little. Please go back to the previous slide. As you know, some areas are rich in biomass. In this area, the utilization of biofuel is an effective option. Then let's look at the partner options. PV will be major power source when the electricity from renewable energy is increased. Most OEMs, including Toyota, are focusing on PV. And Toyota thinks FCHEV is also an option from electricity. As I explained, liquid fuels such as e-fuel and biofuel are options to realize carbon neutrality in some areas. In this case, PHEV and HEV will be utilized. Toyota thinks there's a chance that hydrogen will be utilized with internal combustion engines. We are making a lot of effort on it. I'd like to summarize this slide. PV will be major options to realize carbon neutrality. On the other hand, there are other options such as PHEV, PHEV, which contribute to realize carbon neutrality. From next slide, I would like to talk about the example of our engine development. Please go to the next slide. This slide shows the thermal efficiency history and future target. These black plots show the thermal efficiency of production engines. Our latest TNG engine has 41 thermal efficiency. The engine thermal efficiency for HEV has been top runner. These red plots show the result of research engines. In the research phase, we are achieving 47% with low NOx, and our final goal is 50% with innovative fuel technologies. Today, I will introduce the current technologies and research results for the future, for the near future. Please go to the next slide. This slide shows the result of our latest studies. The outline is shown in the right top. The key technologies are how to ignite air-fuel mixture and how to make a fast flame propagation under the super lean condition. To correspond to them, we are developing the microstratified combustion with controlled air turbulence. As you can see in the left graph, lean limit is expanded to lambda 2.8, and N low NOx can be achieved. And the maximum thermal efficiency is around 40%, as shown in the right graph. We are continuing this challenge in order to contribute to CO2 reduction in the near future. Please go to the next slide. This slide shows the examples of hydrogen combustion. Please take a look at the left here. Y-axis means the index of combustion speed. As you can see, hydrogen has around 3 times faster combustion speed compared to gasoline. As a result, in the right figure, hydrogen leads to expand excess layer ratio, and it means near zero NOx can be realized. Today, I talk about the options for carbon neutrality. It goes without saying battery EV is a major option. And we think the combination between engine technologies and fuel technologies is also an important option to contribute to reducing GHG in the future. Next slide, please. Thank you very much for your kind attention.
Thank you very, very much, Dr. Nakata. And it looks nice and sunny in Japan behind you there. So thank you. And it will save some questions for you for the end, if we may. And moving along now, I'd like to introduce or reintroduce Dr. Ruud Eggels from Rolls-Royce in Germany to give us another perspective on aviation.
Okay, I'm Ruud Eggels, and this slide you have seen before, so we can go directly to the next one. And I will show the vision of our company to the way forward to go to net zero carbon. There will be large similarities what Keith showed because it's aerospace industry, and what we also have been heard, what we also heard before is that it's not driven. It's driven externally, so it's like, can we go to the next slide? And before going to specifically to the aviation specifically, I just wanted to give an overview of the route towards net zero CO2 emissions for the entire company. And looking at the bottom of the pictures, these are like the areas, the units in which we work, and that's civil, that's aviation. We also have power systems, which are also IC engines, so it's a large similarities of what I've seen before of Steve. And okay, sorry, yeah. And then, of course, there's a defense unit system that's also mainly aerospace. And then electrical, that's obviously it's zero CO2 emissions. Well, apart from generating the electricity, of course. And SMTs, like small medium reactors, SMR, small medium nuclear reactors, and that's something specifically of the UK they're looking at. At least you will not emit any CO2 emissions. On the right bottom plot, you see a similar plot as we've seen before, the strategy to go towards net zero 2 emissions in 2050, and partially it's by increasing efficiency, partially is by going to alternative fuels. Of a large part is alternative fuels, and partially also by looking at different fuels. On the right top,
It's a little bit too much detail, but that's looking at different sections like transport, aviation, and energy production, how different technologies will be developed to reduce our CO2 emissions. And the key objective of this slide was to see that with the different sections in which we all work towards the goal of zero CO2 emissions, and there will be a lot of similarities and using similar technologies in all these different sectors. Okay. So also here, a very similar, in the middle, very similar plot as seen before, how we can achieve this achieve our decarbonization strategy. And so we have to look at different kind of technologies to achieve that, and to accelerate the way towards reducing CO2 emissions. And it depends very strongly on the availability and the price affordability of sustainable aviation fuels. This is done specifically on aviation, and we're looking at different parallel paths to go to reduce CO2 emissions. In all the previous speakers, like electric has been touched, and that's something we're looking at as well, but it's also here indicating it depends strongly on the application, similar as for trucks and cars. So electric is something which we already pioneered, and we had already developed some very small aeroplanes which run on electric power, but these were small, and it's only in the range from urban mobility for very small distances to commuters where we think electric can be a solution for the future. The next one is that if you look at sustainable aviation fuels, like more a hybrid system, so it's electric with also combustion fuels. That's something which you also can imagine that it goes up to regional jets. And I quickly jump to the bottom. If you think of long range and wide body business jet for very long distances, then we don't see any alternative than using liquid fuels, and this should then be sustainable aviation fuels. Of course, we're also looking at some concepts where we partially will use electric, so maybe we can use it for the start and landing, or different concepts where the engine is not hanging underneath the wing, but it's embedded within the airplane, and you have electric powers. That's some systems we're looking at. And then the third kind of way to go reduce CO2 emissions is to go to hydrogen. That's an option which is considered in all sections. This is quite challenging to carry the fuel, and I will come back to it later in one of the slides on hydrogen. Fuel cells is also still on there. It's an option. It's some technology where we worked on for quite a long time, and it's still in our vision. But it's still something which needs a lot of development to get to very high power densities, what we need for aviation. I think I skipped this one because I think this is slightly better. Because I now start with the easy bit of using sustainable aviation fuels. And this slide is showing what we have done thus far. And of course, SAF can be a very broad kind of range of fuels, and currently what has been tested is HEFA-like fuels. That's something which is available, and it's almost within a specification of kerosene, and similar to what Guy said before, that's something from a combustion point of view is not so difficult, but that many more aspects for an airplane which is important, like fuel pump ceilings and all these aspects. But what we've done for a range of engines, for the Trent 1000, and we done ground tests with the lean burn system, and the most advanced testing with a Trent engine on Airbus 350, where we flew with 100% SAF fuels to demonstrate it's possible, and we didn't notice any problems. Also for business jets, which is like the key component center of Rolls-Royce in Germany where I work, we did ground tests of the Pearl engines, and also these gave satisfactory results. So the next one is a slide on hydrogen and the different aspects here. So I start with something which is not really clear, which has to be investigated, because it's not clear what the impact is if you switch from liquid fuel to hydrogen. You have much more water emissions, and this will lead to contrails, and these also have a considerable effect on the environment. And a lot of research has been done, but whether in the end hydrogen is better or not, that's not so obvious and not so clear. And what I touched before is like the energy density is something which is key for aviation, and if you therefore, well, the highest energy density you can get with liquid hydrogen, of course, but you have to go to minus 253 degrees Celsius. And then you have an energy density which is still far away from, still not reaching that of kerosene. So talking about, yeah. There's one advantage is like the energy density in megajoules per kilogram. That's 3 times higher for hydrogen, but the density itself just spills it. And then you can either pressurize it or use liquid, and then like the energy in megajoules per cubic meter, then of course liquid hydrogen has an advantage, but actually it's also technically more complicated. So that we also keep in mind that there are applications where pressurized hydrogen could be an option. I think this basically is what I want to say. So these are the high-level targets where we look at how we want to achieve net zero carbon emissions, and we have set targets for 2023 that all our production engines are 100% SAF compatible, and we also want to achieve like live emissions reduced by 35% by 2030. And currently it's a very exciting time because we're doing a lot of developments on improving efficiency to reduce the CO emissions, and also develop new technologies like hydrogen combustion at the moment. So, and then also not to mention these hybrid electric systems is also one area where we're looking at the moment. Thank you very much.
And last but not least, I'd like to invite Sergey Dorofeev up.
Thank you, Roger. Good afternoon, ladies and gentlemen. Do you hear me nicely? Okay, I will try to touch base with another topic which was not mentioned too much in the previous talk, and this topic is related to safety of new fuels, transport, and new energy carriers. And speaking about safety, it is more important to go into details. What does it mean? So when we want to introduce something new fuels and new energy carriers into industry and into public and industrial process, we need to understand hazards associated with these fuels and energy carriers. If we understand the hazards, we need to evaluate what the risk we have to have this in the industrial application and in public. And then we need to, understanding the risk and the hazard, we need to develop loss prevention solutions and safety solutions, such as mitigation measures, safety distances, and other solutions which allow safe handling of new materials. So this is exactly what FM Global is doing, working with industrial application and with our industrial clients. And when we speak about the new renewable fuels, first of all, the most important from the point of view of the hazards is hydrogen blends, such as natural gas per hydrogen, syngas, hydrogen ammonia mixtures. And we need to understand this for variables composition, variables temperature and pressure, and specifically many important understandings still necessary for how to handle liquefied hydrogen. And this is not just vehicles which are involved in using these fuels. So this is energy carriers, there is a production of this fuel, there is necessary transportation of this fuel, and sometimes in big quantity and large distances. We need to use this in power generation to provide electricity, maybe for electrical vehicles. And all of this is important, and this results in a wide range of properties which we need to understand. These new fuels, specifically hydrogen blends, is different from other fuels. So they have different burning velocity, they have different instability limits. They produce different flame heat fluxes to the surroundings. Another important parameter is flame jet blow-off limits is different for hydrogen blends than for propane and gasoline, for example. And it's also different detonation properties in these fuels. And on the picture which shown on the right, it's a photo of what happened recently in Norway. It was hydrogen defueling station explosion, and many believes that it was actually partial detonation of fuel air mixture in this building, considering the scatter of fragments and the pressure wave which was generated. When we look into safety consideration or understanding the hazards of these fuels and of other normal fuels, we have very good understanding of practical combustion property of the fuels which are in use. And for individual fuels as well, for example, we had pretty good understanding of combustion properties of hydrogen. But we do have a lack of understanding of the properties, fundamental properties of mixed fuel at various temperature and pressure. And this is work in progress for this community, combustion community, and I understand that this is a very, very important part of the work, and I was pleased to see this morning how many ammonia combustion papers were presented in the morning. And we will still have a lot of things to do, and I cannot overemphasize the importance of this study in this community of the fundamental properties of new fuels. Because all our safety measures, all our recommendations, they should be based on science, and they should have really good foundation. We also need practical models for safety distances, prevention and mitigation of fires and explosions, which can be used on engineering level and be applied to practice. Now, a little bit about lithium-ion battery safety. It is It is part of the energy carrier, the lithium-ion battery, which is used in vehicles, in transport, and in power storage, and so on. And you know that everybody knows that that there is often, what often happens is thermal runaway, which generate combustible gas release. The gas is it's also mixture of hydrocarbons, hydrogen, CO, CO2, and other components. Depends on the type of the lithium-ion batteries, and some of them are more dangerous for thermal runaway, some are less dangerous, but none of them until now is truly safe. So we still have accidents with any types of batteries, and we need to understand this better. And this is a mixture of two things. We have, if we have ignited unmixed release, we have fire hazard. If we have unignited release and mixing of this fuel with its explosion hazards, we do need to understand this better. And I believe that there is an important piece of work for this community to move forward. I will stop this now, and I will be happy to answer any questions and to go to some other details if you would like to. Thank you.
So I'd like to thank all of our panelists. So I'll look around the audience in a minute to see if anybody's got any questions, but I just want to mention that at the end of tomorrow, there is a session to give people a chance to meet industrial panelists, or at least those who are here tomorrow. And so that'll combine also with tomorrow's industry session. So that's at the end of tomorrow. So I see a hand up in the front there. I don't know how long it'll take to get the microphone there. What I might do is, because we've only got a limited amount of time, I might combine some questions. So I might, go ahead, please.
All right. I'm going to combine two of my own questions.
Okay.
Hydrogen was mentioned as a potential aircraft fuel, especially liquid hydrogen. How is that envisioned to be carried on an aircraft? And the second thing is, ammonia has been mentioned a number of times as a sustainable fuel, but a life cycle analysis of ammonia requires determining the heat required to drive the Haber-Bosch process and the source of the hydrogen, which comes generally from a carbonized source. So how is that a net zero carbon fuel? So two things, hydrogen on a plane, and how is ammonia really CO2 free?
No, I think they're both really good questions. So what I'll do also is I'll slightly widen it out as well, that I'll get several of our panel to talk about it. Because when we talk about hydrogen, there's also this question about whether we have fuel cells or whether we have hydrogen combustion. And that's something I think that some of the panelists touched on as well. So I'd like to talk about that as well. Okay, so I will start, if I may, with Ruud, and then I will go to Keith afterwards. So just because I think the question was principally directed around aviation. So I'll let you have first shot, Ruud, and then we'll go to Keith.
Yes, thank you for the question. Of course, it's a very good question, and it's something we ask ourselves also all the time. And it's also, of course, it's also a political thing which is going on. So we definitely have to, we have no choice. We have to work on the development of hydrogen combustion as an option, and like airframers did all the calculations and see it as an option, that especially for short haul distances, hydrogen is an option for the future, and they want to demonstrate it, and to be able to demonstrate it, they need engines for it, and a short notice. So if you look for a short distance, we're thinking about flight times which are about an hour, and then that is something which is feasible. You can, if you use liquid hydrogen, then it's possible. Then you could make sufficient space in an airplane to store the hydrogen. And even if there are certain, I have to be careful how I say that. There are also applications where you could work with pressurized hydrogen as well.
Okay, if I pass on to Keith, if you're on the line there, Keith.
Yeah, so if you can hear me, yeah, we're going to have to work with the airframers to design systems and hydrogen containers and all this, and figure out where to put it on the airplane, because we can't fit enough fuel in wing tanks, for example. It may be that you'll see fuel carried in parts of the fuselage, but that's really for the airframers to work on. I've seen models of layouts of composite fuel tanks that would be used to carry liquid hydrogen. Then you have to worry about, of course, pumping it, vaporizing it, and feeding it to the engines. So there's a lot of pieces there.
Steve next, and then I'll invite Dr. Nakata on the line as well to comment, because obviously Toyota manufacture hydrogen or some hydrogen fuel cell vehicles. I think it's the Mirai, isn't it? So.
Liquid hydrogen is rather interesting. I worked with it with BMW about 15 years ago, and what they used was a double-walled evacuated type fuel tank. So you filled it with liquid hydrogen, and it was a double-walled system with a catalytic burner essentially to handle boil-off, so that it wouldn't pressurize. But the idea was to minimize the heat transfer so that you could keep the hydrogen as cold as possible for as long as possible. So I would imagine the residence time of the hydrogen in a circumstance like that would be of significant importance. As far as hydrogen on board a commercial vehicle, in the EU, where the tank to wheels is CO2, basically is part of the ZEV mandate, but it's tank to wheels. Hydrogen ICE is something we are considering. In North America, where the IC engine is not allowed by the regs with regard to meeting the ZEV tailpipe requirements, we would be looking more along the lines of BEV or fuel cell. A fuel cell, from our point of view, is a hybrid vehicle. Fuel cells don't load follow as well as we would like them to. So it's essentially an energy source, a power source, and we would use the battery system to manage transient vehicle demand. So hydrogen is certainly part of the potential solution, but it certainly isn't the easiest or cheapest. However, it does give us the range that current battery technology does not. So it's something we do have to consider.
Thanks. If we give Dr. Nakata to give a chance to comment on that.
Of course, we are developing, of course, we have already launched the Mirai with the fuel cell, and also we are making some research on the hydrogen combustion. So we think both have an option to realize carbon neutrality, because sometimes some issues of fuel cell is when the fuel cell is run at the hyper operation areas, maybe the efficiency decreased a little bit. On the other hand, for example, with truck or something heavy duty engines, the efficiency does not decrease so much. So in this kind of area, maybe some chances will remain. So that we are considering the both options. Okay.
I could ask Sergey, related to the hydrogen question, we've got hydrogen combustion, we've got hydrogen fuel cells, we've got all the different storage options for hydrogen, liquid at minus 253 degrees, pressurized hydrogen up to 700 bar. What implications are there for the safety options of hydrogen? Is there a better choice for how we should run hydrogen from a safety point of view?
Different applications would require different loss prevention measures and different engineering solutions. And if we are speaking about pressurized hydrogen as a hydrogen storage in the vehicle or in the refueling station or somewhere else, So that the releases of this hydrogen, uncontrolled accidental releases, can lead to very strong fires and explosions. This is a danger which should be mitigated. I'm not telling that it's not possible, but there are certain measures should be taken to avoid this. Also, the vehicle with compressed hydrogen, for example, tank, if it's got on fire due to accident, is also a danger for surrounding, and this should be managed and mitigated. With liquid hydrogen, it's especially which is used mostly for each plant to be used for transportation of large amounts of hydrogen and maybe storage and refueling station, or transportation on a ship like liquefied natural gas. For example, from Australia, where it generates from sun, and then you want to bring it somewhere else. And it is a very dangerous situation when you have uncontrolled accidental release of this hydrogen during some operation, both on ground and on the sea. And the biggest problem is that liquid hydrogen actually condenses oxygen from air, and then can lead to some bad situations. And this should be better understood, and some work is still needed for that.
It's good that you mentioned shipping, because actually that's probably where our panel, we're not really covering the marine sector. And indeed, I noticed that the questioner also asked about ammonia. And as far as I'm aware, it's in shipping that ammonia is being considered most seriously. So could I just briefly ask everyone on the panel, is ammonia an option? I assume it's not an option in the aviation sector. Is it being considered at all in heavy duty or in passenger cars?
In the heavy-duty sector, I would say no, in the standpoint that it doesn't give us the energy density advantage that we would be looking for compared to BEV or fuel cell. The other challenge is that it isn't drop-in. In other words, ammonia is toxic and it's corrosive. And so a lot of the changes we would have to make on the vehicle and in the infrastructure would be changes that we are going to have to make anyway if we move modes. So it certainly isn't as drop-in perhaps as, say, biodiesel, renewable diesel, even something like methanol or ethanol would be more of a drop-in for our industry than ammonia would.
So maybe, Sergey, can I ask, do you think the toxicity of ammonia is a showstopper for ships?
Well, there is, okay. It's certainly that ammonia is safe in terms of explosion hazard for transportation, but this that comes up to another hazard which should be also evaluated and addressed. And maybe it's less for combustion community, but it's an important problem, this dispersion of ammonia of this kind of releases. This is important task to be solved.
Thank you all very much. I see we've got another questioner who's been waiting very patiently at the microphone there, and I see Katerina there as well. So if we have our first questioner, then we'll have Katerina if you go to the other mic.
Bill Green from MIT. I think it's very important for this community to connect better to the community that's going to actually supply the fuels. Because it really, as was mentioned, we really need an integrated solution all the way from making the fuel to using the fuel, and what really matters is the total emissions and total safety and total cost all the way through. And in that regard, I just want to point out that, you know, back in those charts, we were using coal as our transportation fuel for quite a while, for trains and ships, and even for some cars and trucks. And we switched, not because coal didn't work, but because it's inconvenient, because it's a solid phase. And so I think that fluids are really important, and in fact, stable, safe, storable liquids are really important. And in that regard, I think that liquid organic hydrogen carriers are a thing that really needs some examination, because they would be stable liquids, we know how to handle them safely, and the question is, can we actually make the combustion devices or the fuel cells work with them correctly?
No, thanks very much, Bill. Katerina, if you could ask your question as well, and I will try and...
Sure.
make a composite
Thanks
out
a
of
lot.
them. So.
Katharina Kose, Bielefeld University. So the first question is very simple. I would like to have some real numbers of if you take, you know, there was this inaugurative ship transfer from Australia to Japan in terms of hydrogen on board, how much of the hydrogen did actually arrive in Japan? The second question I have is something which bothers me a lot about everybody getting gleaming eyes about hydrogen. This is that I think that there, in short to mid-term, will not be enough hydrogen for all these purposes that people tend to prioritize. And I would mention that also the chemical industry needs hydrogen as a replacement for some other gases and so on. So if we could think of something like, is there an alternative kind of factor on top of, let's say, local pollution and greenhouse footprint and so on? The dumbest thing would probably to burn hydrogen to heat your home. What's the next dumbest step? Thank you.
Okay, thank you very much. So Bill asked a question about liquid organic hydrogen carriers. So this is where, for example, things like toluene and methyl cyclohexane, in which you're carrying something else around that creates hydrogen. Is that something that any of you guys have seriously considered? I guess not for aviation. I don't know whether liquid organic hydrogen carriers is something that Toyota have seriously considered. I'll let Nakata-san answer that in a minute. I'll let Steve answer first from the heavy-duty sector.
On some level, yeah, I would say we have looked at it. The challenge with a different carrier is that you actually have to have either a reactor or a reformer on board the truck in order to utilize that particular carrier. I would say in a mode of transport where perhaps the infrastructure and the fuel was a little bit more extensive, we're a pretty cost-constrained enterprise. So having a reactor on board to just convert the liquid that you store into the liquid that you're using would occupy a fair amount of space and cost on the vehicle. I guess I would never say that we wouldn't consider doing it, but it certainly isn't the leader in the clubhouse, would be the way I'd put it.
I'll just see if Nakata-san has got anything to add to that for liquid organic hydrogen carriers.
Oh, thank you very much. So maybe in Japan sometimes import hydrogen from Australia. And some companies are considering the liquid hydrogen, and another company are considering methyl cyclohexane. So under the current situation, we don't. I have no idea which is better. But I think maybe now no one can decide which is the best. So now that we have to communicate with the energy importers now. So this is my current answer. I'm sorry.
You'd plea for actually getting a consistent set of numbers around efficiency because, for example, when you're carrying liquid hydrogen, it does tend to boil off, and more of it will boil off than the ship actually requires. So it's pretty tough to go and reliquefy it. So do any of the panel have any comments on maybe how we could regulate to ensure that there's a consistent data set that we could use to actually compare alternative fuels and actually be able to make some sort of objective assessment? So this can be both looking at the looking at both the efficiency and CO2, but also looking at the safety aspects as well. I don't know if anyone, I know that's a really tough question, but maybe if I start with Ruud?
Yeah, I cannot directly answer this question with regard to shipping this for long distance, but it also is an issue for business jets because they may also stand on an airport for a week or so, and then it will boil off as well. So that is something which is known, and I don't know what a solution for it. Yeah. But maybe this question with regard to energy shipping from Australia to Japan is a good question for the next panel because that's on energy. Yeah?
Yes, indeed. Yeah. So for tomorrow's panel as well. So Sergey, I don't know if you've got any comments on a fair comparison between fuels for their safety characteristics.
Well,
last maybe previous 10 years, it was considered different options of what to transport instead of hydrogen. And certainly there are many different variants, and there are some options which may be more attractive from safety, but there are some other limitations maybe there. And as far as I know, that the ammonia transport is for long transport is nowadays the kind of hot topic, and I think it makes sense to find the best way to avoid to have more economic way and to more safe way to transport energy.
So there are so many more questions I could ask, but I think I've been asked to wrap this up by 15:35, so I'm afraid you've had your lot, everybody, but I hope you found it worthwhile. And I'd like to very much thank all of my panelists, both here physically present, and also Keith and Nakata-san, who are online, and I hope it's been valuable for you. So thank you very much.